Welcome to Introduction to Fish Scripting for 3DEC. This is Jim Hazard, 3DEC Product Manager, giving you a relatively short introduction to fish scripting in 3DEC. Fish is a very large topic. We sometimes run a full-day course on it. This is really just the tip of the iceberg in terms of what you can do with fish, and is meant to just get you started. What I'll talk about is some of the basics, variables and functions, fish statements, and then a little bit about lists, and in particular splitting, which is how you can do multi-threaded fish. So as you probably know, fish is the built-in scripting language that gives 3DEC user powerful control over most every aspect of the program operation. The reason it's called fish, it was originally written for our FLAC program, and the language was meant to be called FLAC-ish, like English or Swedish. So it is a language of FLAC, but it has then become, of course, the language of 3DEC and PFC and our other programs. Pretty much every piece of data that exists in 3DEC is accessible with fish, which means that you can use this scripting language to change properties and stresses and query displacements and velocities and anything else you want to do. So it's extremely powerful. It gives you a lot of flexibility to do different things. You can embed commands inside of fish functions, so you could make a loop and do some command over and over again. Common uses for fish are parameter studies. So again, if you want to run multiple models and change some aspect of that, it's relatively easy with fish. Changing the physics. So people will do this where they can change some component of the physics of what's happening and execute some function every time step, for example. Creating your own histories, recording some piece of data over time as the calculation proceeds, applying boundary conditions, and many other different things. So scripting with fish, it's again just a text file. Usually, you're usually writing functions within a text file, so it works exactly the same way as writing commands as we've seen so far. Be aware that fish is case insensitive. So if you're used to C or C++, where the case, uppercase or lowercase is important, that is not true in fish. Capital letters and small letters, it doesn't make any difference. As with the commands, a semicolon denotes a comment. When you're using fish, everything is function. So there's not really an object-oriented style of fish like there is in more advanced languages. This is meant to be a relatively easy language for non-programmers. So everything is functions, and you define your function by saying fish define, write some code, and then put end. And then you can just call the function by giving its name. Of course, you can use functions to call other functions and build up stuff that's relatively complicated. The fish functions that you create are saved with the model save state. So if you define a fish function and you use it, and then you save the state, restore the state, you can use that fish function again. So we use the same text editor that we use for the commands. You can see there's highlighting here. So it's actually quite nice. When you define a function, fish define and end, it puts it in dark purple. Other keywords that are fish specific are in dark purple. So for example, here you can see vector, matrix, and so on. Variables that you yourself define are pink, numbers are blue, strings are green, and so on. And again, comments are gray, just like with the commands. All right, some basics here. You know what? This will actually be easier to just demonstrate inside of 3DEC rather than looking at this PowerPoint. So I'm going to escape out of this. I'm going to start 3DEC. I'm going to make a new project. Now, it really doesn't matter where you put this. but I will just put it with the training materials that you hopefully have downloaded. So there's a fish directory there, number 6. There's a fish exercises directory there, and there's already a fish project in there. But let's not look at that. Let's just create our own project. Let's go up one level and just put it here and call it fish. We can create a new data file as usual here. And again, a data file can refer to commands, or it can refer to fish, or it can refer to a mixture of those two things. And you will often see people having small fish functions within a bunch of commands or vice versa. So let's just call it testing. Right, so again, we've got a blank file. Even when you're doing fish, it's not a bad idea to put model new at the beginning. Now, we can write a super simple little fish function here. Fish, define, and you give the name of a function, call it ABC. And then you can say something like ABC equals 22 times 3 plus 5, end. So here's a function called ABC. It's going to do a calculation and set ABC equal to this number. So this is essentially the return value for this function. If I go to print out ABC, it will do this calculation and print out this number. If I call this function from somewhere else, if I say something about ABC, it will do this calculation and return this number. So I can just print it to the screen. I can say list ABC. The way to call a function is to put its name in square brackets. So what I'm going to do is print the results of calling the function ABC to the screen, and it will appear down here in the console. If I run this file, oh, I did a typo. Let's try ABC. There we go. So list ABC, it returns 71, and it's telling me that 71 is an integer. So that's quite interesting, because note that we did not declare the type of the variable. In fish, again, we are trying to keep it as simple as possible. We do not force you to declare the type of the variable that you are using. So again, if you're used to C or C++, you have to say integer and give some variable name, or double and give some variable name. In this case, it works out what the type is based on what you assign to it. So in this case, 22 is an integer, 3 is an integer, and 5 is an integer. It assumes that ABC is returning an integer. You can make it slightly more complicated. Fish define ABC. If I use the same name as a function that already exists, it will just overwrite it. So we can just create a different variable inside of this thing. So how about HH equals 22? And now you can use that variable in the next equation, ABC equals HH times 3 plus 5, and list ABC. I should get the same answer, right? Because here I'm setting a variable HH equal to 22 and using it in the equation, exactly the same thing I did up above. I just typed in the number 22 here. So if I run this whole thing, it should tell me 22 and then should tell me 22 again. Sorry, 71 and 71 again. Since I've declared a variable inside of this fish function, this variable exists in the world now, and I could actually just print the value of that variable as well as ABC. So I could say something like, I'll just type it in the console here. Let me make the font a little bigger. I can say list HH, oh, sorry, HH, and it will tell me that HH is an integer with the value of 22. Also note that these variables appear over here on the right-hand side. There's a list of fish global symbols. This is totally useful. You can imagine if you have more complicated functions with a lot of variables in it, especially things that might change while you're cycling. You can see the values of things over here on the right-hand side. and it changes dynamically. So if it changes during cycling or any other thing, it will be instantly updated over here on the right-hand side. And this view of fish variables is extremely useful. Okay, this is just some basics about how to define a function and how to call it. Because this is essentially a programming class, it is mandatory that you need to write a function that says hello world to the screen. And so what that would look like, so we can delete all of this. And you could say fish define. And as with other commands, you don't need to type the whole word define. Most of the time, you'll probably just type fish def and give the name of a function, hello. And if I want to print something to the screen, the way I do that is to say io.out. Now, note here, if I make some typos, it highlights it in red, which tells me this is not a real function. This will not work. As soon as it turns into a real function, it becomes dark purple, and I feel good about the fact that I've typed this correctly. And then I give some sort of string in quotes. You can use single quotes or double quotes. It really doesn't matter. So this io.out is a built-in function. IO stands for input-output. There are a bunch of input-output functions. Out is just one of them. F1 works with fish functions in the same way it does with commands. So if I hang over IO and I press F1, all right, if I hang over io.out and press F1, I get information about that particular fish function here. So it says output is string. The variable is converted to a string if it is not a string, and so on. If you want to see the tree of fish functions related to this, so I can open this in the browser. Now I can see the tree here on the left-hand side. So here's the IO utilities. Make this font a little bigger. Right, so there are things you can do here. You can actually take user input or output dialogues and things like that. Most of the time, you're probably only ever using io.out to print something into the console. So here's the function. And I need to call the function again by putting it in square brackets. So I just say hello in square brackets. And in theory, it should print out hello world down here in the console. So let's run it. There it is, hello world. And then it puts in a 0. 0 is because we didn't have a return value for this function like we did with the ABC. The return value is basically 0. It prints this thing out, but it doesn't actually return anything. So it just tells you 0. Okay, let's go back to the PowerPoint for a second. Okay, implementing fish, as well as using the square brackets to call a function, you can also use square brackets to initialize a variable. And in fact, you can put any fish that you like inside square brackets as long as it's one line or one fish statement. So here, let's pretend we have a new model and we want to parameterize the model. So we have a bulk modulus and a shear modulus. We want to put that at the top of the file to make it easy to change later on. Or maybe we want to use this in a loop or something like that. We can define these fish variables inside the square brackets. So we have a fish variable called bulk equal to 1e9. Next line, square bracket, fish variable called shear equal to 0.7e9. Here's commands. So I create a brick, generate zones, set it to be elastic, set the properties. Here, where I'm setting the property, the bulk modulus, I can just use the fish variable to set that bulk modulus again, as long as I put it in square brackets. So I define the variable up here, and I'm using that variable to set the bulk modulus here and the shear modulus here. And this is a very common use for fish. You can define a bunch of variables at the top, or you can even have a bunch of calculations so that the bulk is a function of something. And then later on in the file, when you're using commands, you can use fish variable names instead of actual numbers. Here's a slightly more complicated example. Let's again pretend we made a simple model. We set the zones to be elastic. We've defined two variables here, a Young's modulus 0 and some constant. Here I've got a function, fish define set Young. So what it's going to do, we'll talk about this in more detail later, but it's going to loop through all the zones. It's going to do some sort of calculation. It's going to set the Young's modulus. What's interesting about this example is that there's a command embedded within the fish function. And this is definitely possible, and people do this all the time. So in this example, we're looping through all the zones, and for every zone, I'm giving a command to set the Young's modulus for some particular zone with this ID. Probably you would never do this in real life because there are functions that you can use, fish functions that you can use to set the Young's modulus. You don't actually need to put a command inside of the fish function, but just to demonstrate the possibility that you can do that. And it is quite useful in a lot of cases. Okay, as mentioned, you do not need to declare variables. So if I say a equals 1, it's an integer. If I say a equals 1.0, it's a float. And if I say a equals quote 1.0 quote, it's a string. It just works it out the first time that you use it. Be a little bit careful though, because it's actually possible to change the type of a variable as you go along. So I can say a equals 1 at the beginning of the function, and then later on I can say a equals 3.0, and it turns from an integer into a float. It is possible to force define a type. So again, by default, it figures out what it is, but maybe I don't want to use that default. Maybe I want to force it to be something else. So for example, if I say result equals 5 divided by 2, it sees that 5 is an integer, it sees that 2 is an integer, and it returns an integer, which is probably not what you want. You want 5 divided by 2, which is 2.5, not an integer. So you can force it to be a floating point number. So here I can say result equals float 5 divided by 2, and it will return 2.5. Okay, it is possible to declare local fish functions. And again, instead of looking at the PowerPoint here, it'll be easier to demonstrate in the software. All right, so let's get rid of this hello world function. Let's make a new function, fish define. Well, we can do hello again. This will match the PowerPoint. Say my word equals hello. So I've just declared a variable called my word. It's automatically going to make it a string because I put something here in quotes. I'm going to say end. If I call the function, it will then run through all the lines here, which there's only one line. It will set the variable my word equal to hello. I can print it. It will appear over here on the right-hand side, and I can also print it to the screen. So I can say list my word. Okay, so run that. So over here on the right, you can see my word. The value of my word is hello. It's of type string. When I print it to the screen, it shows up down here. It says hello and tells me it's a string. Fantastic. No problem. By default, all the variables that you use in fish are global, meaning that I could now make another function, fish define test io.out my word, and call that function. My word still exists. It's global. Even though I declared it in this function up here, I can still access it in this function down here. And I can access it in whatever function I want. It's global and it exists more or less forever until I say model new. So you can see that worked. I called the test function and it printed hello to the screen again. Now it's possible to make a variable local to a specific function. And I can do that by just using the word local. So if I do this, I say local my word equals hello, that means that this variable only exists as a variable within this function. This is potentially useful if you have longer, more complicated functions and you use the same variable all the time, like I, and you don't want to unintentionally, set I to something in one function and then it assumes that value in another function. You only want to use I in this function, and then you want it to disappear, and then another function you want to use I again, and you want it to disappear. It's good programming practice to set things to be local if you don't need them outside of the function. So if I try to run this, let's see what happens. I define the function hello, fine. I call the function hello, fine. But then I try to list my word, and it doesn't work, because as soon as this function's over, that variable doesn't exist in the world anymore. It was local to this function. Similarly, if I try to run this test function, that doesn't work either, because it doesn't know what my word is. Okay, so you may or may not want to use this functionality, but when you start writing more complicated scripts, it's not a bad idea to use this local for things that only exist inside of a function. Okay. Obviously, a big part of using fish scripting is doing some math. You have all the usual functions, plus, minus, multiply as a star, divide by as a slash. This little hat is raised to the power of. And then we have a whole bunch of built-in functions that you can use that usually start with math dot something. So tangent, cosine, sine, pi, so on and so on. You can look these up in the manual. This is all pretty standard stuff that you should be familiar with. Just note that math dot something will allow you to use these different functions. Okay, so far everything we've talked about has been general. It's just general fish. You can use the same thing in FLAC 3D or 3DEC or PFC or whatever. There are a bunch of fish functions that are, again, common to all the programs. So things related to discrete fracture networks and geometries and files and so on, math, matrix. But then there are things that are specific to the programs. So 3DEC specific functions, again, are mostly start with block in the same way that the commands do. And there will be block dot something. And then there are some functions related to fluid flow. And then it gets more specific. So you can say block dot something to act on blocks, or block dot zone dot something to act on the zones, or block dot grid point dot something to act on the grid points. And again, there are fish functions for almost all of the quantities that are available and calculated in 3DEC. Not all of them are modifiable. So for example, a grid point position, you can find out what it is using fish, but you can't change it using fish because it will mess up all the contacts and everything. So some of these things are read-only. Most of them are read and write. Okay, we'll talk a little bit more about how to use those functions in a minute. Before we get there, we'll just talk about the control statements. So if you've done any programming before, you will know that common things to do are make a loop, to use an if statement to check if something is true or false. And again, we have the ability to set up commands within fish functions, so that's possible here. There's other keywords you can use to control, like exiting out of a loop, or if, else if, and things like that. So just to dig down a little bit more detail, an if statement looks like this. So you say if something compared to something else, and here are your choices: greater than, equals, greater than, less than, greater than or equal to, less than or equal to, equals. These are all standard. The hash is the only one that maybe you're not familiar with. In the fish world, this means does not equal. You can also actually use exclamation mark equal, which is a more common syntax for not equal to. The older way is the hash. The more modern way is like exclamation point equals. So the syntax looks like this. You say if something, something, then do something. You could potentially have an else, do something else. You can actually have else if, and multiple else ifs to do different things. And then you have to finish with an end if. It doesn't matter if you make end if one word or if you say end underscore if, both of those are valid. And you will see both of those in the examples. Loops. Loops look like this. There's 2 or 3 different ways to do loops in 3DEC, in all the programs. A very common way is to just loop counting up some number of numbers. So it might look like this. This would be equivalent to a for loop in C. Loop local I. So you remember I said if you're using something like I, it's often a good idea to make it a local variable. You don't have to. Loop local I from 1 to n. In this case, n is an input to the function. We haven't talked about this yet, but it is possible to send inputs to a function. So in this case, we're going to sum all of the numbers up to some user-defined value, right? And if you look down here at the bottom, you'll see the user put in 10. So it's going to sum all of the numbers from 1 to 10. I'm going to loop I, which is a local variable, from 1 to 10. I've declared another variable here called s and set it equal to 0. And each time through the loop, I'm going to add I. So the first time through the loop, s starts at 0 and I add 1. Next time through the loop, I add 2. The next time through the loop, I add 3, and so on. At the end, I set the name of the function, which is called sum, equal to the number I was summing up, s. And essentially, that is the return value. So I can say list sum 10. This calls the function, does this stuff, returns the sum of the numbers from 1 to 10. Again, it might be easier to actually just do it in the code. So we can type this out relatively quickly. I can say fish define sum with some input. Let's call it n. I've got a local variable called s, which is 0. I can be lazy here and not type local. I can just say loop I 1 to n. S plus equals I. And loop. Again, as with the if statements, I could type n underscore loop. I can just type n loop as one word. So let's take n underscore loop. Then I set the name of the function equal to the value. So it will return, the function will return that value. And I could print the value that this function returns. So list sum, and I can enter some number 10. I can run this, and it returns 55. Interestingly, now I can see because I didn't make I a local variable, it still exists after I finish running here. It goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 drops out of the loop. So you can see here that I is 11. And then I can see that sum is 55. And it actually tells me that sum is a function. This is slightly confusing. You might ask yourself, why not just do this? Why not say local sum equals 0, sum plus equals 1, and I don't even need to do this line at the end. This will not work because you end up with a recursive function call. So when I'm saying sum plus equals 1, it's trying to call the sum function. I'm already inside of the sum function, and it's a total disaster. So you can't call a function from within a function. It basically doesn't work. So that's why we need to set up a local variable called s, use that to do the summing, and then at the very end, I set the name of the function equal to that, and it will work. So this is equivalent to a for loop in C. We also have a while loop. So another way you could do this function would be something like this. I make a variable called I, set it equal to 0, and I could do something like this: loop while I less than or equal to n, s plus equals I plus equals 1, and loop. So this is slightly more complicated, but just showing you how the while loop works. It's just going to keep on looping as long as I is less than n. So the first time through, I is 0, it does the calculation. Then I becomes 1, does the calculation. Then I becomes 2, it does the calculation, and so on. You need to be a little bit careful here, because if I forget this line 8, this will loop forever, because I will always be less than n, and you end up with an infinite loop. So we use these while loops occasionally, but again, it's often a little bit easier to understand and a little safer to use the other style of loop. But I should be able to run this and it should work and give me the same answer, 55. There we go. Couple more things to say about loops. It is possible to break out of a loop if there's certain circumstances are met, and usually you do this with an if statement. So for example, let's pretend for some reason, if I is greater than 5, I want to break out of the loop. So let's turn this back into the old style, just to make it easier. Loop I 1 to n. All right, so here was our original loop. It's going to count all the numbers from 1 to 10. Now let's pretend that if I is greater than 5, I want to stop counting. So I really only want the numbers from 1 to 5, regardless of what you input here. So I could say something like this. Before I do the sum, if I greater than 5, I can say exit loop. You can see this turns dark purple. So these are valid keywords in Fish. And I can say end if. Remember, with every if statement, I need to give an end if. It's not like Python. It's also not like Python in that you don't need to indent. I advise that you do indent. It makes it clear, what's inside of the loop and what's inside the if statement. It is not necessary like it is in Python. It is necessary to put an end loop or an end if at the end of these things. So in this case, I'm going to send it some number, and it really doesn't matter what number I send it. It's only going to add up together the first 5 numbers, because if I is greater than 5, it's going to drop out of the loop and finish. So whatever the number addition of 1 to 5 is, it's going to return, there you go, 15. A variation on this, imagine I wanted to count all of the numbers, but skip 5. I could do something like this. If I equals 5, continue. What continue does, so exit loop drops out of the loop and comes down here to line 11. Continue skips the rest of the loop, but then keeps on looping. So it will skip line 9 and then go back up to line 5 and then keep on looping. So this is useful if there's certain circumstances that you just want to skip, but you want to keep on looping. So in this case, it's going to give me 55 minus 5, because we're skipping number 5 here. So let's just see if we get 50. There we go. So this is the way to control loops: loop, end loop, exit loop, continue, all potentially useful things. If, end if, I didn't show an example, but it's certainly possible to use else if and else when you're doing these if statements. All right, in the PowerPoint, I here have a exercise for the user to sum all of the numbers from 1 to 100, except for 50. You should be able to do that quite easily now, because we more or less just did it as an example here. Okay, the next topic is lists. Lists are essentially one-dimensional arrays. These are extremely useful. We use them all over the place, especially for storing the variables and the data related to the program itself. So all of the zones are in a list, all of the blocks are in a list, all of the grid points are in a list. So if you're going to use Fish, you definitely want to become familiar with lists. So again, the Fish function, you can create a list, you can append to the list, you can print out all the items in a list, you can loop through all the items in a list, you can do other things you can see over here on the right-hand side. You can find the maximum value in a list, the minimum value in a list, sort a list, so on and so on. And so again, it might be easier, instead of you just staring at this screen, that we can have a look at this within the program and see what happens. So don't get confused. There's a command called list, which is printing something to the screen. And there's a Fish type called list, which is an array. Fish, define, make list. So again, I can declare a variable. Let's just call it my list, and it's a list. So when I do this, I'm creating an empty array. It's an array with nothing in it, right? But I know that it will be an array, so I can go ahead and start filling it up with things. So the way you might do that, let's, for example, loop I 1 to 10. If I want to append to the end of a list, I just say something like this, my list, and I say end equals I times 1.5 or something. End loop, end. And then I can say make list. So I'm going to make an empty list. I'm going to add 10 things onto it. 1 time 1.5, 3, 4.5, etc. So let's run this. All right, you can see over here on the right-hand side, there's a function called make list. There's a variable called my list with a size of 10. It tells you that it's a list. It doesn't list the values, because you can imagine you might have a list with 1,000 things in it, and you don't want to list them all. But it does tell you there's a list of size 10. If you want to see what's inside of the list, you type a command, fish list contents, and you give the name of the variable, my list. And it will print all the things that are inside that list. So at position 1 is a floating point number called 1.5. Number 2 is a floating point number called 3. 3 is a floating point number called 4.5, and so on. I can type it in here just to, so you don't forget, fish list contents, my list. This is totally useful. Once we have a list, we can do lots of crazy things with it. So for example, io.out list.sum my list. Let's comment this out so we don't keep seeing this printed to the screen. Now I'm going to make the list, and I'm going to print out the sum. There you go, 82.5. If for some reason I didn't want to use fish list contents, I just wanted to use fish to print it to the screen, I could do something like this, loop. Now here's the type of loop we haven't talked about yet, but this is super useful, and it looks a little bit more like a Python type of construct. I can just loop over everything in the list. So I don't even necessarily need to know how big the list is. I can just say loop for each item in my list, print out item, and loop. Right, so I've got a list of any size. It doesn't really matter. I'm going to loop through all of the things in the list. Each time through the loop, there's a variable called item, which is going to be set equal to the thing in the list. And I can just print it out. So I should see 10 things being printed to the screen here. There we go. 1.5, 3, 4.5, 6, 7.5, and so on. This is the preferred way to loop through a list. Again, you don't need to know how big it is. You don't need to get complicated than that. It automatically sets item equal to each position in the list. Just to make it clear, another way you could do this would be something like this: loop I one to list dot size my list io dot out, oops, my list I, and loop. So this is how you access individual members of the list. Again, it's just like an array. In C, you would have square brackets here. In Fish, you use round brackets. So it's going to print out my list 1, my list 2, my list 3, my list 4. Notice that the lists in 3DEC and all the ITASCA programs start from 1. So again, if you're used to C or C++, where arrays start from 0, that is not the case here. They always start from 1. So the first entry in the list is entry number 1, and then it's going to print entry number 2 and entry number 3, and so on. So if I run this, I should see these numbers being printed twice because I'm using the for each loop, and then I'm using this loop. Right. So here, blah, 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 up to 15, and then blah, 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 down to 15. There we go. So that's really the basics of lists. This for each construct is what we use when we're looping through things in 3DEC. So for example, if you want to loop through all the blocks, you say loop for each. The local here is optional. It's just creating a variable called BP, looping through the block list, and each time through the loop, BP is equal to one of the blocks. So the first time through the loop is block number 1. The second time through the loop is block number 2. Third time through the loop is block number 3. Same thing with grid points. Same thing with structural elements. Virtually everything that exists in 3DEC is stored in one of these lists, and it's easy to loop through all of them by using this for each. So on the next slide, here's an example exercise, just to show you how you would use something like this. We create a block. I'm using this model random 10,000 because, well, let's just put it into a 3DEC model and we'll talk about it. Right. Let me exit out of this. Let's go back to 3DEC. There's a few new things in here. If you've been following along with these tutorials, there's a couple things here that you may not have seen before. So model random 10,000. There are certain operations that occur in 3DEC that rely on a random number. One of them is zoning. So remember, we fill up shapes with tetrahedral zones. There's some randomness to that zoning. Every time you run the model, you might get something slightly different. If you want to ensure that you get the same thing every time, you want to specify this random seed. The random seed is just any number. It recommends that it's something close to 10,000, but it really doesn't have to be. You can go over here and check the help section. Model random I, set the seed for the random number generator. By default, it's 10,000. But every time you hit model new, it's going to give you a new random seed. So if you want to make sure you get the same thing every time, you can force it to use a specific random seed. Okay, we do that in this case because we're going to apply some randomness to the jointing. Block tolerance 0.001. If you haven't necessarily got to this point yet in the other tutorials, the tolerance is used to decide the size of the block that's going to be cut. So you can imagine when we make cuts in 3DEC, it's possible that the cut might come very, very close to the corner of a block. You don't necessarily want to end up with very, very tiny blocks in your model because it will cause problems with your time step and convergence and things like that. So there's a default tolerance that makes sure that you don't end up with very, very tiny blocks. Sometimes you want to use a tolerance that's even smaller than that. In this particular case, we're going to choose something smaller than the default. And this is an actual distance. In this case, let's say it's meters. So 0.001 is actually 1 millimeter. It's not a relative value. It's an absolute value of distance. Okay, I'm going to create a brick. Seen this before. I'm going to cut a joint set. Seen this before. What's different now is I'm giving a dip with a mean value and a standard deviation. So the dip is 45 degrees and the standard deviation is 5 degrees. So this is where the randomness comes in and why I set the random seed. It's setting up a Gaussian distribution of dips with a mean of 45 and a standard deviation of 5, just to make this problem more interesting. Same thing with the dip direction. A mean of 120 and a standard deviation of 5 degrees. We give a spacing with a mean of 1 and a standard deviation of 0.5. So what this is doing is cutting an actual joint set with a spacing of 1 meter on average, but there's some variability there, with a dip on average of 45 degrees and some variability, and a dip direction of 120 with some variability. There's one joint set. Now we're going to make another joint set. I'm just going to copy and paste that. In this case, the dip is 75 degrees. The mean, the dip direction is 270 degrees mean. Spacing is the same. So if I run this, oh, I need two numbers for the brick size, obviously, a minimum and maximum. Here we go. Does a bunch of cuts. Even with this small tolerance, you can see here that it actually rejected at least one cut, probably because it would have been too small. But for fun, we can go and make a plot and just see what we created. Add the block. Right, so there's a crazy looking block with two different joint sets in it. You can see there's some variability in the dip direction. And also the spacing. The reason to create this slightly complicated model was because let's pretend now this was a real project and I created this model and I wanted to find out what the minimum volume of block is. So you can imagine with this randomness, I could potentially end up with some very, very small blocks in here, right? One of these little guys here. Whatever reason I might want to find out what the minimum volume is. So I could do something like this. Fish define get min vol. I'm going to loop through all the blocks. And it's super easy. Is just do this. Loop for each. Give a variable name. It could be anything. I use BP for block pointer. Block.list. So all the blocks in the whole model. I can check the volume like this. I can say vol equals block.vol BP. So this is a function, takes a block pointer, returns the block volume. And loop. And if I call this function, we'll loop through all the blocks, and it will get the volume for every block, but it doesn't do anything with it. So it's actually not very useful right now. So what we need to do is keep track of the minimum volume as we go along. So I'm going to create a variable here called minvol, set it equal to some humongous number, 1e20. And then I can say if the volume of this particular block is less than the minvol equals vol. End it. So for every block, it's going to check that the volume is less than the minimum so far. And by the time I get to the end, I will have the minimum volume of all the blocks. If I run this, call the function, I could set it up to print it to the screen, or I can just look over here on the right-hand side The minimum value is 3.9344 e minus 9. So you can see here why I might want to have a function like this. I've ended up with at least one block that is super tiny, which could potentially be problematic. Slightly more concise way of doing this, instead of having this if end up, you could do something like this. Minvol equals math.min of minvol, comma vol. So what this does is it finds the minimum of minvol and vol and sets that minvol equal to that. So we can replace that if, calculate something, end if, with just one line here, which gets the minimum of these two values and sets minvol equal to that. And I should end up with the same thing here. (3.9 e minus 9). So this is just a relatively simple example of how you can loop through all the things in 3DEC. Okay, the last topic is splitting. Splitting is a way to run fish functions multi-threaded. This is relatively new in fish. You know, if you're running a function like the one we just did, you don't necessarily need to speed it up. I mean, you only probably run it once and it goes quite quickly. Often people will run a function every step or every 10 steps. They'll want to loop through all the zones, for example, every step. That could potentially be very slow. So if you can do this in a multi-threaded way, that is super useful and allows you to speed things up. The way to do that, so ignore the first few lines here and jump down to where it says fish operator. It's actually really easy to do this. Until now, you've seen fish define function name for each something, do a calculation, end loop, end. If you get rid of the loop and the end loop, and you change fish define to fish operator, and you send it as an input, this grid point, and when you call the function, you send it the entire list at once, and it intelligently takes that whole list of grid points and splits them up onto various processors, calls this function simultaneously on each processor, and does what it needs to do. It's super easy. Again, you just get rid of the loop and the end loop, send it the whole list, and it will automatically do this for you, multi-threaded. It's slightly confusing if you're accessing global variables and things like that, because you don't want the different threads to stomp on each other. But for something simple like this, where we're just calculating the port pressure of every grid point based on its position, this multi-threading works great. There are other forms of splitting here. So again, just as one single line, if we look at this one here, I'm making a list of the x coordinates of all the grid points. So again, almost every function in 3DEC, you can send it the whole list, rather than just an individual block pointer or a grid point pointer. So I send the whole list to the gpos function and get the x coordinate of that, so the x component of that. I send it the whole list, and it's going to return a new list of all those x coordinates. Again, the syntax is just : the whole list, and it will basically execute this in a multi-threaded way. You can get even more complicated. So for example, I want to find all the zones that have a given group name. The function would be zone is group. Again, I can send it the whole list. I can send it the group name that I'm checking. Without going into too much detail, what this actually does is return a group of Booleans to say, whether they're in the group or not. And I want to turn this back into a zone list. And so at the end of executing this function, I end up with a list of zones that are in this group, and it does it in a multi-threaded way. The syntax here is a little bit confusing. You can read about more in the manual. The splitting is totally useful. These operators, the syntax is not confusing at all. It's super easy, and I recommend you use this whenever you're looping through things. Not only is it faster because it's multi-threaded, it's actually less typing because I don't need the loop and loop here. Okay, that's the end of the introduction to fish scripting in 3DEC. There are many other topics that we could talk about. Things that are totally useful, file reading and writing. We do that all the time. Tables, geometries, and by geometries, I mean like triangulated surfaces, vectors and tensors. If you are returning the displacement or the position of a grid point, you can return that as a vector, and you can do things like get the magnitude of the vector or subtract vectors or add them and things like that. Same with stresses, you can get a tensor, do operations on the tensors. Extra variables we didn't really talk about, but it is possible to add data to the system. So for example, the grid points have a displacement and a position and a velocity and so on. You may want to store extra data on a grid point that is not by default given to you with 3DEC. So you can make your own extra variables and store them and calculate them and plot them and things like that. This is extremely useful, and people do that all the time. And almost everything you can do with fish, you can also do with Python. I'm not talking about it in this session, but there may be a future session talking about using Python with 3DEC. Okay, thanks for joining. That is the end of this presentation.